chapter, passive filters, and we examine transfer function, filter classification, low pass filters, high pass filters. Now we are examining these band pass filters. What is inside the band pass filters? There are a simple band pass filter filter is a second order circuit. It has got one inductor and one capacitor in it. When it is first order circuit, we had low pass or high pass filters. So the degree of the circuit has been increased to pass to band pass filters from low pass high pass filters. So there are two of them. In this video I will be examining this one, find out the transfer function, define new physical quantities depending on lower and upper cutoff frequencies, and then analyze the same circuit in Pro Tools and how to do a synthesis based on these analysis I'm going to explain in this video. The next video is about band reject filters. These band reject filters are very similar to this one, therefore there is no video for this one, band reject function, so you could study your own. So let's go in the details of these band pass filters now. We've got to move to open board now. Yeah. This one. Let me clear it first. So you see here, there is a serial RLC circuit. If you get the output from the resistor, you end up with a band pass filter. This is our claim. We've got to show it now, whether it is a band pass filter or not. In order to see that, what we could do, we're going to find the transfer function. We know the transfer function directly determines the filter characteristic of the circuit. So here is the transfer function. How are you going to find that? So we have done similar things before, so I'm not going to do it step by step, but I will tell you how to do it. So these are serial connected three elements, so the equivalent impedance is R plus SL plus 1 over SC. So if you divide that VIS to that equivalent impedance, you find that current. If you multiply that current with this resistor, you're going to get V0S. From that, you can get this transfer function. So if you replace S with J omega, this module of this transfer function here is changing like that, and the angle of that transfer function is changing like that. Now you see this is the second order. So if you look at here, central frequency says when the imaginary part of this is equal to 0, that means this is equal to 0. You see what it is, omega L minus 1 over omega C is equal to 0. So that means omega L is equal to 1 over omega C. That means omega square LC is equal to 1. That is omega square is equal to 1 over LC. 1 over LC. Then omega is equal to 1 over square root of LC. So this is called cutoff frequency, central frequency. When it is cutoff sorry, this is central frequency or resonance frequency. This resonance frequency makes this impedance equal to 0. When this equal to 0, then your circuit becomes a resistive circuit, isn't it? When this is 0, so your transfer function is going to R over R. That means your transfer function is equal to 1, isn't it? So it is a special frequency. We call it central frequency. Cutoff frequency, as we defined already, the maximum value of the transfer function module is equal maximum value over square root of t. If we have an equation like that, then our omega becomes the cutoff frequency. Since it is a second order equation, we are going to get two cutoff frequencies. There are going to be some negative frequencies as well, but negative frequencies has no meaning. In physical world, negative frequency has no meaning. Positive frequencies has the meaning, so that's why we have two cutoff frequencies. Second order, we've got two cutoff frequencies. The values of cutoff frequencies, if you do this operation, you're going to end up with these values. So it is very similar. In here, this part is negative in here and positive in here. The result is always positive. You could see it here. Here the square under the square root. We've got the same thing here. If you add something more positive, so the result of this is going to be more positive than this value. So omega C1 is positive and omega C2 is also positive. So these are two positive frequencies, and these are the cutoff frequencies, because when it is substituted, you're going to get that equation. H max is equal 1, of course. That is in the central frequency case. So we've got a central frequency here and cutoff frequencies in here. So from this equation, you could see that relationship between central frequency and cutoff frequency is this. You can prove that. Omega C1, C2. Multiplication of those two upper and lower cutoff frequencies, square root of it gives you the central frequencies and frequency. So we can say now that this central frequency is this frequency, which is in the middle, that one. These cutoff frequencies here, these cutoff frequencies are these cutoff frequencies. So if you find the difference between these two cutoff frequencies, upper and lower cutoff frequencies, you're going to get the bandwidth. That's better. That is better. And is equal to this one. So you can write it in terms of element values. So this again, once again, cutoff frequency in terms of element values. Sorry, the central frequency in terms of element values, cutoff frequencies in terms of element values, bandwidth in terms of element values. So you can easily say the bandwidth do not depend on the capacitor value. In here, cutoff frequencies depends on 3 of the element values. Central frequency do not depend on the resistor value. It depends on the L and C element values. And the last one, physical quantity that we are going to introduce, is the quality factor. Once you found the central frequency and bandwidth, central frequency over bandwidth gives you, in terms of element values, gives you this. This is also a measure for the quality of the filter. Why is that? If this is smaller and this is the higher, that means your filter quality has been improved. Now we've got 1, 2, 3, 4, 5 elements, 5 measures related to the filter. The basic measures are these upper and lower cutoff frequencies, 2 of them. So if you know these cutoff frequencies, then roughly you know your characteristic, bandwidth filter characteristic. The other terms, central frequency, bandwidth, and quality factor, are the physical quantities which says something about the filter. In practice, we've got 2 basic characteristics, which are the cutoff frequencies. For the bandwidth filter, it is upper and lower cutoff frequencies. Now, once we have done analysis like that, we can do a synthesis based on analysis. Not this one, maybe this one, okay. Let me clear this area. Keep this, maybe that will be useful. So in here, previously we examined that if RLC elements are connected in serial and if you take the output from the resistor, the rough characteristic of the transfer function is this, isn't it? We already found that. In order to see that, we know the topology of our circuit, we know the input and output values, and the element types are also known. There is one resistor, one capacitor, one inductor. But if somebody asks us, design a filter, a band pass filter for me, of which cutoff frequencies is this, then we could do this synthesis for this demand. How we are going to do it? Our problem, since we know the topology and element types already, so what is left is to find out the element values. If you find out these element values, that means we can say that we synthesize a band pass filter of which cutoff frequencies is 1 kHz and 10 kHz. So how we are going to do it? Easy. You know this central frequency. Central frequency is this. We already know that. So if omega lower cutoff frequency and upper cutoff frequencies, these are known. But this is F, you see, lower cutoff frequency, and this is upper cutoff frequency. In order to find this central frequency, that is angular frequency, so we've got to write this omega lower cutoff is equal to P 1000 and omega upper cutoff frequency is equal to P 10,000. And then use that formula, you end up with this value here. So we already know that for this case, the central frequency is resonance frequency is equal to this one. So this helps us. This is going to be equal to this, isn't it? So there are 2 parameters here to be calculated, and there's one equation. That's good news because I can choose one of the element value as I like and then calculate the other element value. That facility of selection is good for engineering. So that means I can choose the right element value. How I'm going to do it, as we said already, the capacitor values, standard values are limited. There aren't so many standard capacitor values available in the market. So we start from the capacitor. So capacitor value has been chosen as 1 microfarad here. Then we can calculate the L value. L value after that calculation becomes 2.5 millihenry. That's a reasonable inductor value. It's good news. If it is not reasonable, that means you're going to play that capacitor value in such a way that inductor value is the one available in the market. How we are going to calculate the resistor? So we could use that formula here, because since I know the omega 0, this is the central frequency, over the bandwidth. Bandwidth is the difference between those two, so bandwidth is 9,000, isn't it? I know the central frequency. Central frequency is this. So I know Q. On the other hand, I know this is equal to this. So in here, we already found that capacitor 1 microfarad. So we can calculate R value. If you do this calculation, you end up with 143 ohm. So this is a reasonable resistor value. If you choose these resistor values as, this is not that one anyway. So if I choose a capacitor like that, inductor 2.5 millihenry and capacitor 1 microfarad and the resistor 143 ohm. So now we are saying this filter, if you take the output from the resistor, the cutoff frequency is going to be 1000, lower cutoff frequency, and higher cutoff frequency is going to be 10,000 hertz. That's F. And this value, this is the highest value, which is 1, and this is 0.7.707. So that's the band pass filter that we found. Similarly, this, for example, is the alternative one. Once again, the elements, there are 3 elements, but we are taking the output from the parallel connected LC elements. This is going to be another band pass filter, and all this transfer function has been calculated here. So you could make your own example if you like. That is the outline of band pass filters. Either this one or this one. Transfer function is this one and this one. You can write the transfer function in terms of the parameters that we already introduced. That's the band pass here. So your transfer function is going to be like that. This is your central frequency. There is a condition here. If the upper cutoff frequency is much bigger than the lower cutoff frequency, then you can write this as a transfer function. So once you know the transfer function, so you can easily say these parameter values just by looking at the coefficients in your rational functions transfer function. Okay, that's the end of this video then.